Hello everyone. I'm Korean, so I cannot speak Chinese. So this presentation is in English. Please understand. And the topic is to compare the junction temperature measurement method. In this paper, there are 4 measurement methods. And I'm Andrew Yang, and I'm application engineer for power module industrial field. The power module is gel field. And this is outlined. The first is introduction, including the background, this paper, and then the simple explanation for these measurements. And the second is the what is the 4 junction temperature measurement method, and the third is the comparison of the data and the results, and then the conclusion. First is instruction. This is very simple module, and look at this one. This is the power pin, and this is switch like IGBT, and this is DBC, so top copper and ceramic. So when the voltage applied to the pin to pin, the current flow like this one, and the current flow pin and IGBT and wire and the pin again, and then the device is heating up. Each device is heating up too. And then if there is high current or over current, then the device is exceeded the guaranteed temperature like 175 degrees Celsius. So if there is some very big happens, so damage die. So it is very important to set the proper junction temperature for the device and to a safe operation. So it is very important to measure the accurate junction temperature in the real system. But as you know, it is very hard to measure this because every module has packaging, and then it is very hard to measurement point or the sensing the real junction temperature. So this paper, there are 4 measurement methods, right? Estimation and the simulation and the real measurement. The first is just calculation. It is the hand calculation, the very simple one. And the second is simulation. The popular simulation tool is iSpectrum as ANSYS. And the third one is using the thermocouple wire on the device. Directly they attach the thermocouple wire. And then using the thermal camera. It is, we provided these 4 solutions or for support to customer or the system level companies. Yeah, so there are 4 measurement methods, estimation and the measurement. And the next thing is 4 junction temperature measurement methods. Before that, I set the target device with our power module. It is this application is solar and ESS product and a high power level. And we called this product is FIBP. BP means that base plate. Look at this one. This is case, and under this one there is base plate. Because it is very big module, so to attach the module on heatsink well, then we should high torque on this device. And it is very helpful to attach the heatsink. In this module, there is the IMPC topology. IMPC is the multi-level inverter circuit, and the target device is T1. T1 is 1000 volt and 200 ampere IGBT in 3 parallel. And this is first method for calculation. The base equation is first thing, the thermal resistance is delta T divided by power loss. Yeah, in that time, delta T is junction temperature minus heatsink temperature. And then based on this second equation, that we can induce this one. Junction temperature equals these parameters. So if we want to get the junction temperature, we want to get these 3 parameters. So RTH, means that from junction to heatsink thermal resistance, this value is measured by the T-thermistor. And then heatsink temperature is the fixed temperature with the chiller. And then power loss is 150 watt. And then very simple, then we can get the junction temperature is 110 degrees Celsius. But in the previous page, the target device is 3 parallel, not a single device. So this calculation is just to show that very ideal condition. So it is very hard to affecting the thermal coupling by each device, and then it is very hard to apply the considering parallel operating. And the second method is simulation. Simulation is used ice bath, and the heat sink temperature and power loss is the same as calculation. This is IMPC module. Before that, we should understand what operating this circuit. This graph is just the power factor 1 situation, and power factor 1 means that all DC to AC conversion. So, and in this time, I focus on this half sine wave, positive half sine wave. In positive half sine wave, there is 2 paths. First is powering DC to AC through T1 and T2, and then freewheeling D5 and T2. In that time, I used the powering mode like this. The current should flow then T1 and T2 together, and then this is simulation result. And there, look at that. This is T1 and this is T2. This is the 3 parallels. So current flow like this one, and this here, and throughout this one. So T1 is heating up and T2 is heating up too. To simulation, we put the power loss equally in the 3 devices. The total power is 150, so one device is 50 watts for this simulation. So one device is heating, T1A is heating up, then T2B is heating up too, T1C is heating up too. So T1A is heating up, then this heating temperature affected to T1B. This is thermocoupling. So the result is the T1A is 107.7 and T1B is 109.8 and T1C is 109. Look at this, the T1B is higher than T1A and T1C because the T1B is more affected by thermocoupling effect with T1A and T1C. But there is one, not a great one, because there is no wire and there is no pin in this simulation model. So current flow is pinned to IGBT and the wire, and it makes the thermal coupling all around. So wire and the pin, there is no wire and pin, so the thermal coupling effect is lower than the real module. And then next thing is measurement with thermocouple wire. Before that, we should understand how to put on the TC wire of the device. This is device like IGBT and something. And then we apply the epoxy for isolation or protect isolation voltage. Because if there is no this layer, then we put the TC wire on this point directly, but the voltage is collected to emitter like several hundred voltage. If there is not enough the isolation voltage level of recorder, there is some damage at the equipment. So some users want to get this epoxy layer. So after that, I put the TC wire on this layer, and then this edge point is the target point, measurement point. After that, the TC wire should be fixed. So pour more epoxy to fix that. And then this process to apply the 3 devices like this. This one is T1A, T1B, T1C. All same process using this point, this point, this point. And then test is ready. Then the next one is test. This power supply is to turn on the T1 and T2. And chiller is make the fixed temperature like 85 degrees Celsius. And the multimeter is to measure the voltage drop from collector to emitter to set the power loss to 150 watts. And this is current wire because this is continuous current flow, this T1 and T2 to make the power losses 150 watt. So this TC wire is attached to recorder. So after that, we can get this graph. This point, the temperature is high, temperature is increased like this one, and then after 600 seconds, the temperature slightly increased. After that, there is a saturation. And I put this value, and the T1A is 114.7, T1B is 116.8, and T1C is 115.7. The trend is very similar to similar from the simulation result. There is a thermocoupling effect, and T1B is more affected than the T1A and T1C. And in this real module, there is the wire and pin and DVC design is different, the simulation. So there is the very high impact on the junction temperature. So simulation and TC wire temperature gap is about 7 degrees Celsius. And the last thing is the measurement with the thermal camera. Before that, we should prepare the black sample because thermal camera is infrared camera, and infrared camera is very important to emissivity of this one. The emissivity is one of black, so black color is very good accurate to measure temperature. So this sample should be prepared before the measure with thermal camera. And making process is similar to the TC wire. First, they apply the isolation layer, and then spray out the black color on the surface like this. After that, put the module on the chiller, and the tested sequence is very similar to the TC wire. After that, we can see that. There's these 3 devices, and we can see the old thermal distribution. But the previous page, the TC wire measured only 1 point, not 2 or 3 or multiple points. So with the TC wire is some disadvantage for this. In previous page, look at that. The TC wire is only 1. So we cannot measure this point, this point, this point, this point. So we cannot see the thermal distribution. If TC wire put on this point, then we can measure this point, this temperature, not this point. So the accurate is less than the thermal camera. So the result is the T1B is the maximum temperature 120.8 degrees Celsius. It is higher than the junction temperature with the TC wire because in this time we can see we can see the temperature distribution, and we can catch out the maximum temperature, not any specified point. So it is better to measure the TJ max value. And the third is the comparison for measurement of results. There is 4 results. First, the calculation, simulation, TC wire, and thermal camera. The calculation value is 110, but this is a very ideal condition, and cannot consider the parallel operating. And there is no thermocoupling effect. So T1A, B, C is same junction temperature. But simulation, so we put the power, but the power is equally. But this power can make temperature, and this temperature can impact on the thermocoupling effect each devices. So the center side is the highest, 109.8 degrees Celsius. The other is the lower than this one. And the TC wire like this, the maximum temperature 116.8, but this cannot see the temperature distribution on device surface. So it is very up to the designer. If designer set this one, there's different temperature. And then thermal camera is, we can see the temperature distribution, so we can catch out the maximum temperature. So in the test result, the thermal camera shows the highest junction temperature, and it can show that the accurate junction temperature, maximum junction temperature. But I think a thermal camera, to put the thermal camera with the real system level, it is very difficult. So many system level company want to get this TC wire sample. It is very easy to measure the junction temperature because the wire, put out the wire and then connect the recorder is very easy. But temperature gap is just 4 degrees Celsius. So I already recommended them to, if they use TC wire, then should add 4 or 5% margin. Then it is quite similar than thermal camera. But before the real test, some users want to get the junction temperature because they want to check the feasibility, their system. So some customers want to get the simulation result. And then the simulation result is lower than the real measurement value. So we should put the 10% or the 11% margin always. After that, it is quite matched well. But in future work, we should make the good summer model to simulation, and then we compare the real junction temperature or real measurement value. This is the next future, next item. And calculation, I do recommend it. But it's a very simple thing. So just want to see the very high junction temperature or not. So in my opinion, then thermal camera is a correct one in this table, and then TC wire and then simulation. But if user use these two methods, then they should add in some margin. And last is conclusion. The conclusion is just mentioned that in this paper there are 4 measurement methods and the calculation is simple. But the accuracy is not good. But the simulation, is quite better than the calculation, but there is the thermal model is very impact on the real junction temperature. And the real measurement with the thermocouple wire and thermal camera is better than the other things. And if the user want to use the simulation or with the TC wire, then they should add some margin. And the conclusion was done. But we always recommend the real measurement via TC wire or thermal camera. Okay, that's all. Thank you.